1-2B. Today, we are going to be focusing on a lot of the terms that you learned yesterday. Was that yesterday for you? This is what period? Third period. It was yesterday for you. A lot of those terms get used to give us postulates today. And a postulate sounds like a big fancy term. All a postulate is something that we know to be true. Okay? Some brilliant mathematician back in the day did a lot of work to prove that what I'm telling you today is in fact true. We don't have to prove it. Eventually you'll prove some things. Those are theorems. Postulates, we just say, yep, we know they're true. So, postulate 1-1, don't memorize the number. That's a waste of your time. I just need you to understand the concept here. Okay? What it says is this. Through any blank points, there's exactly one line. We're trying to put a number in there. What do you think? I heard 1, I heard 2. 2. It's 2. Good job. Through any 2 points, there is exactly one line. If I were to put 2 points on my paper here, the only line that I can draw through those 2 points is this one here. Oh, not that one. Should have put my points closer together. We got it. Okay, through any 2 points, there's exactly one line every single time. That leads us to, potentially, an intersection. Intersection, what do you think of when you hear intersection? What? Someone said something. What did you say? Cars, yeah, totally. Driving, right? There's an intersection at 183rd and Dumont. Okay? Or there's an intersection at Palo Verde and Artesia. It's where things meet up, right? This road meets up with this road. Well, in geometry, it's no different. It is where things meet up. So we're looking for a commonality, something that is the same about our 2 figures, our 2 lines, our 2 planes, whatever it is that we're talking about. So we're going to do some intersecting here with this postulate 1-2. This one says if 2 distinct lines, so 2 different lines, can't be the same line, intersect, they will intersect in exactly how many points? If 2 different lines intersect. Exactly one line. I know what you're thinking 4, because you're thinking 4 ways in the intersection, right? 4 sides. But here's the thing. There is one point that they have in common. And that's what we're looking for. What do they have in common? If I draw a line here and a line here, okay, their intersection is right here. Does that make sense? 1 point. Where they meet is 1 point. They intersect. We'll call this point E. Okay, so if this is A and B and C and D, we would say line AC. What's another way you could name line AC? CA, AE, EA, right? They're all the same line, okay? Line AC. Can you name the other line for me? DB, line DB, or BD, or DE, or BE, right? Those 2 lines intersect at what? Point E, right? They meet at 1 point, exactly. So at point E. Okay, that's an intersection. So 2 lines will always meet at 1 point. All right, third postulate. This one tends to be a little harder to wrap your brain around for a couple reasons. Do you remember what we learned about planes yesterday? What do you know about a plane? They're flat. It looks like a parallelogram, right? It looks like this when we draw it. What else?
They don't end.
They don't end. Okay, so that's the issue, right? There is no end to a plane. So if I'm treating my floor like a plane, if I'm trying to visualize it, I'm going to see it as my floor. But we need to visualize it as if it keeps going, right? Okay, so my floor is a plane. This postulate says if two distinct planes, so two planes now, so maybe my floor and my wall, okay? If those planes intersect, so meet up, have something in common, they intersect in exactly one line, okay? It's tempting to say segment because the plane ends here and the plane ends here, but planes don't end, right? Planes keep going, therefore their intersection must keep going. So here's what you can think about, right? Here's my floor. We'll do my front wall so you can all see it a little better. Where they meet is this edge, right here, and it just keeps going. That's our line of intersection, okay? So two planes will always meet in a line. Questions on that? Okay, then I want you to turn and talk to someone near you. Find somebody, okay? Don't be bashful. Those of you that have people to work with, find someone who doesn't have someone to work with and invite them in, okay? I want you to see if you can figure out where plane ADC and plane BFG intersect. What type of thing is your answer going to be? A line. Okay, so you're looking for a line. What line do these meet at? All right, what do we think? BC? Anyone get something else? BC. Okay, here's how it goes. Oh, I should have paused. That's okay. Plane ADC. Okay, here's A, here's D, here's C. What plane in this cube is that? Front, back, left, right, top, bottom? The top, right? That's our top plane. So that's this plane right here. Okay? Plane BFG has B and F and G. Which plane is that? Right. The right side. So you're looking for where does the top meet the right? It's two planes, so it's going to be a line for your answer. Your intersection is right here. So BC or CB, okay? But it's a line because it keeps going. It looks like a segment, right? It looks like it ends. But do planes end? Therefore, does their intersection end? No, okay? So intersection of two planes is always a line. Did you try the next part? Two planes that intersect in EF? I didn't tell you to, so it's okay if you didn't. I'm going to erase my shading, and we'll chat about that. Anyone have an answer? Two planes that intersect in EF. ABE and EFG, is that what you said? Yes. So if you look, EF is here. So you're looking for what two planes meet up right there. Well, that's going to be the bottom one, right? And it's going to be the front one. So you can just name your bottom and front planes. Bottom plane, how many letters do you have to name a plane? 3. Can you use more? Mm-hmm. So if you like to do all 4 corners, because that just makes you feel like, yep, I got it, that's fine. You can do E, F, G, H, okay? If you want just 3, you can do 3, and it can be any 3 in any order, okay? Now, when you name a plane with more than 3, then we go in a specific order. Doesn't matter which specific order, but you wouldn't go E, F, H, G, right? If you're going counterclockwise, keep going counterclockwise. If you're going clockwise, keep going clockwise, okay? It just helps you to see what that plane is a little better. How would you name the orange plane? ABF, ABFE, AEFB, okay? Any of those work. It's whatever you see, as long as it's the right thing that you see. All right, questions on that? Okay. Then we have postulate 1-4. This is my favorite postulate, at least of today's lesson. Through any blank non-collinear, first of all, what does non-collinear mean? Not in a straight line, okay? Not on the same line. Through any blank non-collinear points, there's exactly one plane. How many points do you think you need for exactly one plane?
2.
Oh, I hear lots of answers. Okay, who thinks 2? Who thinks 3? Who thinks 4? The masses got it. It is 3. Through any 3 non-collinear points, there's exactly one plane. So here's the deal. Think of my fingertips, okay? Are my fingers all the same length?
No.
When they're in a line like this, I cannot put a plane through all 3 of them, right? Now, that's not to say you can never win 3 points in a line, because you can sometimes. But as soon as I make sure they are non-collinear, it does not matter where I put those fingers, I will always be able to put a plane through them. Let me show you. Straight fingers, they can all touch the top of the desk, right? The desk right now is the plane that my fingers go through. Now, if I rearrange my fingers, I put my 4th finger way down here, I can still touch all 3 of them to the desk, right? Think of it this way. Any of you into photography? Like still shot photography, you would use what to make sure you have a stable shot?
Tripod.
A tripod, right? They don't use 4-legged stands for photography, because what happens when you add a 4th point? It wobbles, right? Have you ever sat on a stool in the science labs? They're terrible. It's so annoying. They wobble, right? So 4 points doesn't have to have one plane, but 3 points, you will absolutely get one plane through it, okay? So with that in mind, you should be able to give me some planes here. You can do all 3 of these on one figure. I'm gonna copy because I want a second figure. So if you wanna make a quick copy of this and drop it down below, you are welcome to do that. You don't have to, but the middle one is kind of funky. I'm gonna put that one on the second, okay? And I'm gonna color code because it's what I do. All right, so in example 2 here, it says what plane contains points N, P, and Q. So take a look. Here's N, here's P, here's Q. Top, bottom, left, right, front, back. Which plane has all 3 of those points? The bottom, okay? What's your 4th point if you had to put a 4th point with it? R, yeah. So the plane that contains all of those points is this plane right here. Okay, now I'm gonna jump down here to the 3rd one because I'm gonna put it on that same thing. What plane contains M, L, and Q? The back, right? You have M, you have L, you have Q. You could lump R with it again. If you just connect all those and shade it in, that would be your back face. Do you guys know what the dotted lines mean? Dotted lines aren't visible, right? They're the ones in back. They're the hidden part of the figure, okay? Okay, so then this last one is a little bit funky because it's not the plane that you're looking at. I'm gonna do this down here. J, M, and Q. So here's J, here's M, here's Q. Where's your plane? What do you mean in the middle? Yeah, diagonal. What would your 4th point be that is associated with those 3? P, yeah. So if I were gonna put a plane through those 3 points, it would be actually through these 4 points like this, okay? It's kind of like if I take my Kleenex box, right? If I have these 2 points up here and I have 1 point down here, the only way to get through all 3 of those is to cut my Kleenex box diagonally in half. Okay, so that's where your plane would fall on that. Questions on that? The end. It's good, right? Love it. Love it.